Good afternoon, everyone. Welcome to today's webinar. We have Nitriding Your Dyes, saves money and improves quality, and our presenters are Richard Dixon of Hydro and Yahya Mahmoodkhani of Castool Tooling Systems. I am your hostess, Lissa Nelson of AEC, and I'd like to remind you that all your computer, audio, and telephone lines are muted. If you have any questions during the webinar, please select Q&A from your toolbar and type your questions in the dialog box. I'll present the questions to Richard and Yahya when they are done with the presentation, and they'll be able to address those then. If we run out of time today, you can always reach out directly to Richard or Yahya or me, and I'll see that they get your questions. Just to briefly tell you a little bit about our presenters, Richard Dixon has been in the extrusion business for almost 35 years, formerly with Alcan, and for the last 20 years with Hydro Aluminum. 4 years ago, he took a post of Director Customer Training and Development for Hydro Aluminum Metal Markets North America, after serving as Director of the Hydro Aluminum North American Technical Center for 7 years. He has been an active member of the AEC Die and ET seminar committees, and he also serves on several Aluminum Association and ASTM technical committees. He is also the editor and co-author of Hydro's Die Design and Manufacturing Manuals. And as a leader of Hydro Aluminum's international die team for many years, he drove the effort to create and refine ever more productive die designs. Richard's passion remains advancing extrusion beyond its current limits through understanding and education. Richard was our Volunteer of the Year award winner at the annual meeting in 2014, and we really are honored to have him with us today. With a PhD in materials engineering from University of Waterloo, Yahya joined Castool as a process simulation engineer in June of 2019. He has been continuously involved with industrial research projects on aluminum extrusion since 2008. Yahya worked closely with Rio Tinto, GM, Ford, and Castool, mostly on improving the extrusion of aluminum alloys for the automotive industry. Yahya is now a product development scientist at Castool, always seeking challenges to make extrusion better and better profiles faster. We are honored to have Yahya with us as well today, and now it's my pleasure to turn the webinar over to Richard and Yahya.
Greetings, everybody. Another day, another webinar. We'll just get ourselves started here. Yahya, I don't know if you realize, but you're muted.
Yeah, I know. I just let you start.
Okay.
Thank you.
Okay, I'm trying to get the slides to progress. I'll get there in the end. We're trying out this time because we're remote because of COVID. We're trying to have, there we are, both of us having control of the presentation at the same time, which is a first for GoToMeeting as far as we're concerned. So just as a quick introduction, these are all things we all know, but there's going to be PDFs and things like this passed around of this, so I want it to be complete. The extrusion die is a critical component in the process. It makes the section shape. It generates the majority of the surface quality, and really the critical element for the die in terms of shape and these things is the bearings. And what we're going to address today is how we treat our bearings. Let's just look at the cost of these things. A general extrusion plant has about 3,000 dies somewhere sat in racks per press line. Well, that's a very average number. There's more and more or less, but in general extrusion, there's a large number of dies out there. And even if it's a 7-inch press with a mix of hollows and solids, you're going to come out about an average of $1,000 a die. So 3,000 dies at $1,000 a piece is one hell of a lot of net operating capital. It's a lot of money, and we need to make sure we get the best value out of those dies. And we can reduce our costs by extending the useful lives of our dies. I do put a small codicil in here. We really should extend the lives of our dies, but without sacrificing productivity or recovery. In fact, what I like is dies which are higher life, higher productivity, and higher recovery. And they exist, you just have to work hard at it. Now, an extrusion die lives in a really quite aggressive environment. There is an enormous hydraulic machine pushing solid but hot aluminum through it. And the die operates under very high loads and at very high temperatures. And so that this works, the die steel has to have hot strength. It has to retain its hardness at extrusion temperature. There's no point in it going soft after a couple of hours at 1,000 degrees, because it's going to be spending most of its working life at those temperatures. It needs to have some toughness. It needs to resist crack growth. I've seen a lot of dies with little micro cracks in them. And good steel, those micro cracks don't grow too large, and they don't really cause the die to reach the end of its life. We need impact resistance. Those dies get bashed pretty hard sometimes. That's without people taking sledgehammers to try and get them out of the die rings, which always makes me cringe slightly. And we need good wear resistance, because we need them to withstand abrasion and adhesive wear in the extrusion process. And what we're looking for ideally is a process that we can apply to our dies that will increase wear resistance, but without messing any of the other properties. And that process, which is currently the most popular for doing that, is nitriding. So really that's our sort of introduction as to why we're going to talk about nitriding. Just a little bit of history. I always like to dig back. My favorite book is Lau and Stenger Extrusion, published by ASM in 1981. Section 5.5.5 is on surface treatment for tools. And the first bit is the service life of nitrided dies is far superior to that of untreated dies, and very good results have been obtained, in particular in aluminum extrusion. A die life of 3 to 6 times that of the un-Nirtided die has been realized. So that's 1981, we knew that. And the other quote from that section 5.4.5.5 is the dies, therefore, have to be removed and cleaned after about 150 to 200 extrusions, and then can be successfully re-nitrided. This operation can be repeated several times, provided the die does not have to be taken out of service for cracks. So that pretty much defined things, and I think 1981 was a big year for you, wasn't it, Yaya?
Yeah, it was my birthday.
So Yaya was born when this book was published. So
yeah, so
if you'd known you were going to be an extrusion man, you should have had this as a birth gift.
Yeah, thank you. Yeah, nitriding is a steel is good.
Yeah, so just to show, this has been around a while, but the techniques of die making, the techniques of looking after dies and all these things have changed significantly, as Yaya has changed in the past 30 years. He doesn't look like he did when he was born, I'm sure. So things do change, and we need to look really today at the things that are applicable to us. There are 2 reasons that bring a die to the end of its life. I call them commercial reasons and technical reasons. A die can be too low a productivity to make it worth running. It can be too low a recovery for various reasons, be it front and back scrap or for bad surface, or it could be too high a weight per foot. If you're selling a section by the length, you really don't want that section to be heavy, because you're giving away all that aluminum. So a lot of extruders I know will retire a die because it's too heavy running. Some dies are scrapped for technical reasons. They're broken. If you look at a die plate and you count the number of pieces, and if you get to 2, it's probably broken. That was early advice I had. But we have dies that consistently give bad shape or bad surface due to some defect in the die, and that can also bring the end to a die. But for good dies that are running out there, the important thing is the manufacturing quality of the bearings, which has improved dramatically in the last 30 years. And more importantly, the evolution of the bearing during die usage. And that was the subject of an ET paper I gave back in 2016. And the mixture of this bearing quality to start with and how we treat it really are the key factors in defining the life of the die. Why do we want nitriding? Well, during extrusion, steel is relatively soft. H13 is particularly good at retaining its strength at high temperatures, which is why it's called a hot working steel. but it still is relatively soft compared to a hardened steel at room temperature. Inclusions in or around the billet, pieces of dirt that got onto the container with the billet come through and can scratch the bearing and cause damage. And the big thing though is that iron and aluminum really like each other. And Yaya is going to tell you later on exactly how much they like each other. But this leads to adhesive wear. Aluminum sticks to iron, and when you break it away, it sometimes takes a few iron atoms with it, and that's adhesive wear. There are also things, though, that go onto the die outside of extrusion. In the die shop, bearings are polished after it's been through caustic. Some people take that polishing a little over enthusiastically and can damage the bearings. Walls can be opened up deliberately to get some section into tolerance. And in that process of either polishing or correction, the bearings can get rounded. This leads to shape changes, the surface deteriorates, and the die really is on a slippery slope down towards the ends of its life. If we nitride, we put this protective hard layer on the surface of the steel. And that protective hard layer means that the steel is a little bit harder, at least the bit on the end of the bearing which is nitrided. Inclusions will do less damage to it because it's hardened. Iron and aluminum, when there's a nitrided layer in there, actually don't have the same affinity, so there's less adhesive wear. It also means that when you're polishing the die in the die shop, the bearing is more resistant to your polishing. So it's a good thing all around. Over to you, Yaya.
Okay, thank you. So there, as Richard said, there are two main mechanisms for bearing wear. One is adhesive wear, second is abrasive wear. So we know that all the aluminum alloys, we're not talking about the pure aluminums. Like aluminum alloys, they're like a composite material. They have like these tiny hard precipitates or inclusions in them, so that we cannot avoid them. They are present in all billets. So when the aluminum is passing through the bearing, so the soft aluminum is passing and it's carrying with it like those abrasive hard particles. So they will do like a sandpaper. It will do abrasive wear. But the aluminum itself, which is soft, how it wears which is the main type of wear in the bearing, adhesive wear, which is done by soft aluminum. So why it does that? Because aluminum adheres to the iron, and then in the next slide I'll show it how more adhesive it has compared to other metals with iron. So soft aluminum can wear the hard die because the chemical reaction or solubility of aluminum in iron can affect that. So special steels can help. So special materials like H13 or hot work tool steel that they can retain the hardness up to 600 degrees C. And nitriding the surface will improve it to the good extent, maybe 3 times or up to 6 times better in wear life. And also speed and temperature. Aluminum alloy is also effective, but increasing the speed and temperature dramatically will increase the wear. So as I said, bearings are hot. They can reach 600 degrees C, which is tempering temperature of the hot working tool steel, such as H13. And then it will temper the H13 so that when the H13 tempers, no matter what is at the surface, even if the nitride layer, if the H13 tempers to below 40 Rockwell C, the nitride layer will peel off, and then you'll touch the surface of the steel without the coating. Okay, this is some experiments done using a hard ball touching the surface of the softer material, and they push it with some force to make some deformation in the soft material with the hard material. So in this case, the hard material is iron, and in the soft material can be different metals. And it's showing how much force is needed to rupture that adhesion that has been between the hard, strong material and the weak material. So for iron to iron, it's the biggest. It's no surprise because iron to iron, it makes the diffuse into each other and it makes it so that the same material. After that is iron to aluminum, which is a 2.5. So if you compare the aluminum to copper, for example, the adhesion force between the aluminum and iron is double the adhesion force between iron and copper. So aluminum adheres very strongly with the steel. That's why we have adhesive wear. And I put like a aluminum iron phase diagram here to just show how much aluminum we can dissolve in iron without making a new phase. For example, alpha iron, it has up to 20% capacity to dissolve aluminum in it. So that's why aluminum can diffuse into iron and then make a new phase or dissolve in the iron, and then so the bounding line or the boundary will disappear very fast. There's another bounding called thermo-compression bounding. If aluminum is under pressure with iron at higher than 400 degrees C, which is always the case in extrusion, it makes thermo-compression bounding. How it happens, it is when you have atoms of aluminum diffusing into the iron and atoms of iron diffusing into aluminum because they're dissolving each other. And then your boundary disappears. And then when you try to separate these two materials from each other, the hard material, which is iron, can take a little bit of aluminum with it. But when there's a lot of aluminum moving on the iron, so like the bearing, it sometimes can happen reverse. So the aluminum can take some of iron with it. This is why we have washouts in the bearing. This is a picture from Rio Tinto showing that the bearing has washed out because of adhesive wear. This area of the bearing is where you have aluminum is sticking and then moving and it's sticking, and when aluminum sticks, it sticks to the material, and then it makes that thermo-compression bounding, and then when it moves, it grabs a little bit of the material from the surface with it because it sticks to the surface. And then after a few extrusions, there might be some severe adhesive wear and washout in the bearing. This is looking at that surface with higher magnification. You can see that the beginning of the bearing and at the end of the bearing, it's better than the middle. Middle is where you have that transition zone. And then at the end of the bearing, you have like just, sliding the material over it. So which is only abrasive, no adhesive. So why do we nitride again? So we increase the bearing hardness. With increasing the bearing hardness, we decrease the friction and also adhesive force between the aluminum and the surface. So it improves the wear resistance. How much we can decrease the friction by nitriding? This is just this research done by Siat et al. In 2015. They're showing the friction coefficient for nitrided and un-Nirtided, untreated material. So untreated material is the black line, and untreated material is the red line. With this, you're seeing the friction coefficient here, and then the black line is a nitrided material. So for the nitrided material, the friction coefficient is about 0.5, and then for untreated, it's about 0.7 to 0.8, which is a huge difference. And then you can see that the wear in terms of material removed from the surface of the die made of 42 CrMO4 is about 21 versus 3, maybe 7 times more wear in untreated versus nitrided die. So it can last maybe 7 times more than a untreated material. So we talked about adhesive wear. Now Richard is going to talk about abrasive wear.
Thank you, Yaya. Yeah, adhesive wear is actually a big subject on its own. So we've just covered it here very lightly, just the fact that we want you to be aware that there's this form. Abrasive wear also goes on. And abrasive wear and extrusion, the most common hard particles that do damage are things that are actually stuck to the outside of the billet. I've done a lot of examinations over the years of people who sent dies into the tech center saying, we've got a big inclusion stuck in this, take a look at it. And quite often it's a bolt or a chunk of steel from somewhere in the press line that's got into the container. Everything that goes in the container has to come out, and it has to come out through the bearings, most of it, apart from a small butt end. So I've seen a lot of die bearing damage done by road dirt, pieces of concrete. The particles inside the billet, if the billet has been properly homogenized, tend to be much smaller and a much lower chance of doing any damage to the bearing. It's the bigger chunks of stuff that are the problem. But for abrasive wear, the main source of abrasive wear in the die is when it gets to the die shop. When it comes out of caustic, it needs cleaning because there's a residue, and people polish these die bearings. I have to put forward that it should not be anything harsher than ANSI 600, which is ISO 1000 paper for polishing. We've had several webinars on this, and I made presentations in ET paper. There's a lot of very good data that shows if you are wanting to polish the bearing, you shouldn't use anything more aggressive than ANSI 600. The reason I say ANSI and ISO is, believe it or not, there are actually 4 different standards for grit of abrasive paper. And the 2 common ones in the US are ISO and ANSI. I believe the ISO one tends to have a P number. So P1000 is equivalent to ANSI 600. But we subject our dies in our die shop to sandblasting and to extrude hone. And we really need, whenever we do anything to the dies off the extrusion press, we need to really show a duty of care to those dies, because those bearings are critical elements for things we want. Now, we're talking here about polishing and cleanly only. If you want to change the shape of the hole, you want to move the bearing, put a choke on it, put a relief on it, or open up a gap, then you need more aggressive paper because you need to remove some steel. The theory behind using the lighter grade papers is you're only removing the dirt, you're not removing the steel. And since we want to keep the steel, that's good. But if you're going to do a die correction, basically you need to remove steel, so you use more stuff. Quickly through then, use the right paper for polishing dies in the die shop. There's an ET paper at ET 2016. If anyone wants it, drop me an email, I'll send you a copy. Keep the logs and billets free from dust and dirt. But most importantly, and of course the subject of today, is to have a regular nitriding and re-nitriding schedule and stick to it. If the die is only good for another 15 billets for its due its nitriding schedule, then only run 15 billets. It can be a fine balance. If you overcook these dies either in preheating or in use, you can be pretty destructive to this nitriding layer, even though it is a good strong layer. And we strongly recommend that you calculate your time between nitriding intervals, not on number of billets, not on pounds extruded, but on the length that is extruded through the die. Because if you're pushing a little tiny thin section, you'll get a much longer run out on that cavity than if you're pushing a great big heavy 2-inch bar. So it's not pounds. Let's do our re-nitriding schedules based on extruded length. So there are 2 tricks really to getting your nitriding right. We've explained to you kind of why we need nitriding. Let's look at how we do it and how it works. The 2 tricks you need to know is 1, getting the nitrogen in the surface. Now, N2 nitrogen, which is every time we draw a breath, 80% of what we draw in is nitrogen. It's a molecule. It's made up of 2 nitrogen atoms. They are too big as a pair to go into the surface of the steel. We need in our nitriding process to make atomic nitrogen. That's atoms of nitrogen available to diffuse into the steel. That diffuses in pretty good. The N2, the nitrogen molecule, which is in the air around us, it doesn't diffuse into steel at all well. Good job, really, because we make containers to hold nitrogen of steel. So I don't know how we hold nitrogen if it could diffuse through steel. And then the second thing is using that nitrogen in the right way. Just making atomic nitrogen on the surface of the steel isn't really good enough. There are, of course, temperature and time considerations which have to be taken into account, and Yaya will deal with those in just a minute. But for the moment, I'm just going to talk to you about getting the nitrogen into the surface and molecular and atomic nitrogen. Now, historically, there have been lots of ways of nitriding die steel. Salt baths, fluidized beds, gas nitriding is the most popular at the moment, and people have tried ion beam and plasma. Each one of these has its downsides and its upsides. Salt baths, molten baths of liquid cyanide are not very popular today with the EPA or the European equivalent, and I think I only know of maybe 1 plant still using salt bath nitriding for dyes. Fluidized beds, they're still pretty environmentally unfriendly. But gas in a sealed container with the exhaust gases subjected to a flame on the way out to burn off any ammonia, that's pretty good from an environmental viewpoint, but it's challenging to control. And back in the early days of gas nitriding, there was somebody there with a calculator and controlling a little flow valve for each of the gases that was going in and calculating his dissociation constant and then adjusting them. Well, the computers came along. And computers can control this now, and people will sell you computer-controlled gas nitriding systems where they can control the nitriding potential really very accurately and automatically for you. Ion beam and plasma nitriding, it's exciting stuff. It does a great job. The problem is the nitriding particles come from a single point source. So you can have shadows. And if you have a narrow channel, which dyes are full of, you can't do both sides. One side will be in the shadow. So really, it's great for some uses, but it's not good for extrusion dyes. So the rest of the presentation, we're going to look at gas nitriding. It's pretty much the industry standard method now, and we're going to look a little bit about what's important to control. I've already said we need to get the right mix of our gases. That's ammonia, hydrogen, nitrogen. These are molecular hydrogen and molecular nitrogen. This is all part of controlling the chemical environment around the surface of the die to get the reaction we want to happen. And that reaction makes us atomic nitrogen. The number 1 most important thing I want you to remember from this presentation is that reaction occurs on the surface of the steel, in that very, very, very close to the surface, fractions of a thou from the surface. The reaction occurs, the ammonia, the nitrogen, and the hydrogen all touch the steel, and at that point, atomic nitrogen is made. And some of it diffuses into the steel, and that's good. You've got some problems, though, if that steel isn't clean. So you need to understand that steel is a key part of the reaction, and we're going to cover this about how many dyes you load and all these things. It's really important you pay attention to that. Some of the nitrogen, atomic nitrogen, diffuses into the surface, and some of it just reacts with another nitrogen next door to it and drifts back off as gas. So here's a little bit of a schematic of what we're looking at. ammonia, NH3, right, with the right balance of nitrogen and hydrogen, because this is a dissociation reaction. So if we bump up the amount of hydrogen and nitrogen gas that's in there, we slow down the dissociation of the ammonia. So that's how we trick the system to run at the speed we want it to run at. And the product of this dissociation reaction is a nitrogen atom. Now this nitrogen atom is produced here on the top of our beautiful blue aluminum. I guess that's because it's hydro blue. But we make our nitrogen atom here. And some of them, they go out and they just become, joins another one and it becomes a nitrogen molecule and disappears off. But some of them start to go into the surface. About 5% of them will react with things like chromium and manganese and other elements in the steel to make hardened particles. And some of them will just go in there and disrupt the matrix and form this diffusion layer. This is the process that's going on inside your nitriding tanks every time you run your dye. And this layer here, this surface layer, is where all the really important stuff happens, where this dissociation reaction occurs. And I have to stress, it is N, nitrogen atoms, that we want. This N2 here, that's a waste. It just goes away. And we use the chemistry of the gas to try and control so we make as much N as we can. Now, there is, like all things in material science and metallurgy, there's a phase diagram for nitrogen in steel, and it makes different phases. Yaya's going to cover that technically a bit for you in a minute. But this nitrogen diffuses into the surface. Now, we're looking here at 3 different profiles of hardness we could get. This is the edge of the steel. This is the depth going in. We want to see, when we do the first nitriding, we tend to get a curve like C. Good hardness on the surface, but it's not really got any depth behind it. I believe that's how people describe the Detroit Lions running backs. There's a couple of good ones, but there's no depth behind them. Sorry, I have to live in Michigan, so I have to hear about the Lions all the time. B has got a bit more depth, and A is got a lot of depth. If you start to get any wear in the surface, you really have to go quite a long way before you start to see softer steel that you see in this profile. So we're looking for nitrided profile A from our process. And here is an example of how nitriding progresses. These are curves of hardness going from the surface in. You can see how it's done here, little micro indenters. And we go in, and depending on the size, you can see here at the surface, the little pyramid that's being knocked into the surface is much smaller hole than the pyramid's being knocked in here. You measure the size of the pyramid, and that tells you how hard the steel is in that position. You can see big pyramid, getting smaller, getting smaller, getting smaller, getting smaller, quite small. And that's what this graph tells you. High hardness going down to about a 600 Vickers when you get into this area here. What we want is we want more depth. So you can see at 2 hours, we get this much depth. At 3 hours, this much. 4 and 5. At this point, you don't see a lot of difference between 4 and 5, but when we look down at the critical area, which is where the gray goes into the dark gray here, you start to see that at about 3.75 thou, at 2 hours is our total case depth. At 3 hours, that's gone out to 5 thou. At 4 hours, it's gone out to about 5 3/4, and at 5 hours, it's gone out to 6 thou. So we're pushing the nitrogen deeper and deeper in. Now, what's happening is that nitrogen, which is inside the material, is diffusing both inward and outward. So this is a schematic of what we've just seen. This is some hydro data collected by my colleagues. After the first nitriding cycle, we get very similar hardnesses at the surface. But after one cycle, you can see it drops off here over 50 microns, which are for the second, I think it's 4 thou. My brain just died on me. I'll come back in a second. But over 50 microns, we've lost all the hardening. On the third nitriding cycle, some of the nitrogen, which is in here, oh, something went wrong there, yeah. We didn't get our nitrogen movement. Okay, doesn't matter. I'll try and verbally explain it. A nitrogen atom, which is sitting just here, when it gets hot in the next nitriding cycle, it can go to the right, it can go to the left. It randomly moves. But the ones that go to the left, once they break this surface, they'll meet another nitrogen atom, boom, nitrogen molecule, they're lost to us. The ones that go inwards just increase the case depth. They just push the case depth inwards. So after 5 nitriding cycles, provided we've done everything else right, we have a much, much deeper case depth that looks a whole lot more like that sketch that I showed you at the beginning, which is our ideal case depth. We don't want to try and do this in one go, because as Yaya is going to demonstrate to you, if we try to get too aggressive in pushing that nitrogen in, we produce the wrong phase. And I'm sure some of you have seen dyes which have gone crazed or brittle because of it. This is another graphic. This is showing the difference between a used dye and an original dye. The dye, when it comes in, has got that nice hardness profile we show. But with use in the press, with numbers of times through the dye ovens, those nitrogen atoms near the surface, they may not move as fast at 800 degrees Fahrenheit in a dye oven, but they move. And the ones that go out the surface are lost forever. So this will drop down. And this happens to the dyes in use. And this is why it's important we re-nitride them. We push that back up. Here is some data taken from hydro. And this is the blue line, is the profile of a first-time nitrided dye. Looks pretty good. If we did a surface indent on it, it's good and hard. We put it in a dye oven for 24 hours, and this is what the profile looked like. We've lost all of this. The amount of time you keep your dyes in the dye oven is really quite important. The second reason it's important, apart from just losing the nitrogen, is that you can form iron oxide on the surface of your bearing. And when Yaya told you there's a 22 meganewtons required to pull apart iron and aluminum, if you put some iron oxide in there, you greatly increase that number. There is a strong, strong affinity of aluminum to try and fight the iron for the oxygen atom. And that can cause some things. In fact, if you've ever seen YouTube videos on the thermite reaction, you'll understand. If you haven't, I suggest you try Googling thermite reaction. There's some people out there demonstrating how it works. But if you mix iron oxide and aluminum powder and throw a match in, that's how they repair welded railway lines. You make liquid iron to weld the line. So it's a very, very strong reaction. Oh, there's my little nitrogen moving backwards and forwards on this one. So the nitrogen near the surface, if it diffuses inwards, it can move backwards and forwards in here, and some of it goes deeper. The nitrogen at the surface of the steel, it comes out and there is no way back, because now it's an N2 and it can't fit. So the way we treat our dyes after we've done our nitriding is very important. We don't want to lose that valuable nitrogen we've put in there by leaving a dye in the oven for 24 hours or a week. I think the worst I've seen, I found a dye in the oven after 6 weeks. It was a very interesting conversation with my press crew as to why the dye had been in the oven for 6 weeks, but basically nobody wanted to run it because it was always a bad running dye. And I can tell you after 6 weeks in the oven, it was going to be a bad running dye. It was a self-fulfilling prophecy. But you need to respect that dye heating time.
Yeah, that also explains why we always promote single cell dye ovens over chest ovens.
Well, they give you a better chance on bigger diameter dyes, that's for sure. It makes a big difference about how long it takes you to heat them up.
Yeah.
Anyway, Yaya is going to talk to you now about using the nitrogen in the right way. I've told you how we make it. Over to you, sir.
Okay, thank you. So there are 2 tricks to nitriding when getting the nitrogen into the surface, or molecular nitrogen versus atomic nitrogen. So and using that nitrogen the right way, the right amount of nitrogen at the right temperature. The reason is, I will go to the next slide first. So we have, this is the iron nitrogen phase diagram. And then these are different phases that can be made between iron and nitrogen. So the left side, when you see Fe, is mean 100% iron, and then 1%, 2%, 3%. At the 6%, around 6%, we have a phase about at between 400 to 600 degrees C. We have a phase called gamma prime, which is the phase that we want. It has right amount of nitrogen in it, which has a good combination of hardness and toughness. If you put more nitrogen into the environment, you're going to end up with having epsilon phase, which is about 10% nitrogen, and it's brittle because it's too hard, but at the same time it's too brittle. We don't want it. If it's less than that, you're going to end up with the alpha iron or some compounds with less nitrogen in it, or gamma iron, which has less nitrogen in it, is less hard. So we don't want that. So the gamma prime is the one we want.
So yeah, it's just like extrusion. It's time and temperature, right?
Yes, exactly. And then this temperature, it should be right at the right range, and also the concentration of the ammonia in the mixture to make the right phase gamma prime. And so this is looking at the surface of the nitride layer from the this is a cutted surface, and then so you're looking from the side. So this is actually the surface layer. And then if you go a few thous underneath, you're going to find diffusion zone, and then from there you're going to have transition zone with your transitioning to the core, and then the white area is the base steel, which it's also called core. Between the core and diffusion zone, it's the transition zone. It's very important. If you have very thin transition zone, it means that your nitride layer is not being bounded well with the base metal. You're going to have cracks between it after a couple of like thermal shocks or heating and cooling. And then the best practice is to have like a very thin white layer and thick enough diffusion layer, because if the diffusion layer is too thick, I'll show you what happens. You may end up having cracks all over, and then these cracks, if they get bigger than a critical size, it can grow into the base metal and then fail the whole thing. So the good case thickness is about nitride thickness is about 6 thou. Okay, as we discussed, there should be a different temperature range and different ammonia contents or volumetric concentration in the environment. You'll get different phases. So as I said, alpha is soft, epsilon is brittle, gamma is made in high temperature. It's not made in low temperatures. And then the gamma prime is good. But it's made in the lower temperature. It's slow, but it's what we want. So we better work in this range to make sure that the steel is not softening or tempering. And at the same time, we have to, control the volumetric percent or concentration of the ammonia in our mixture, gas mixture, to make sure that we get gamma prime, not anything else. If it's too concentrated, we're going to go towards the brittle. If it's less concentrated, we're going to get soft nitride. So we have to make sure. Okay, why this is so important because if we make brittle means phase at the surface, if we get gamma epsilon instead of gamma prime, this is what happens. So that the surface is going to be
This is
brittle.
where one of those hardness indenters have made a pyramid, and you can see that pyramid has been driven into the surface to calculate the hardness. These two hardnesses are very similar, so the pyramids are the same size. But on the left-hand side, there's no cracking, and on the right-hand side, there's cracking when you drive the pyramid in. And you actually sometimes see this when you're doing tests on these surfaces. Sorry to interrupt you there.
No worries. If you look at those two and then just look at the surface, you're gonna see the same thing in both. And if you just run like the hardness test, you're gonna have the same hardness test. But if you magnify the hardness indenter more to see what's happening around it, that's where you notice that if you have epsilon, it's going to be brittle. You're going to have to see something like this to make sure that your nitriding is done properly. This is not good. Okay, so first we need to do the right chemistry in the gas, the right mixture of ammonia, hydrogen, gas hydrogen, and gas nitrogen. So the reason that N2 does not go into the metal is because the N2 is a molecule and then it's big. It cannot go through the atoms of iron. It cannot diffuse through it because it's too big. So it has to be at atomic nitrogen. Atomic nitrogen has almost the same, very close atomic size to iron. So it can just diffuse between the iron atoms and then diffuse into the matrix. And we need to make the atomic nitrogen. This is made on the surface of the steel, as Richard said, not in the environment. It's just it's a surface. The steel surface is a catalyst for this reaction. The nitrogen diffuses into the surface. This is where the hard layer is made. But we don't need very thick hard layer because it also makes it brittle. The chemical activity all occurs at the steel gas interface. So what happens if there's a layer of grease or dirt on the surface? I think Richard is gonna show us in the next slide. Yeah.
This whole nitriding business is very key on the amount of steel that's in the reactor. If you put just one dye into your nitriding reactor, it ain't going to work very well, because all this dissociation constants for breaking the ammonia up and making nitrogen is based upon the volume of steel inside the reactor. So a lot of places I've worked in will keep a whole load of scrap dyes, which they just use to fill up the reactor if they don't have a full charge that day. That way they keep the amount of steel in there. Those also have to be cleaned, by the way. So what happens if you've got some dirt on the surface? Well, this is just a great piece of data from Rio Tinto. Thank you, Rio Tinto, for permission to use this. But it's if you look here, there's a whole load of different bearing preparations: wire cut only, wire cut hand polish, sandblast, extrude honed but not cleaned, extrude honed, alcohol cleaned, extrude honed, polished, and then sandblasted. And if we look, the two outliers that really have a big impact are the orange and the purple square. So that's polish and extrude honed but do not clean, and extrude honed and do not clean. This is because the extrude honed is a waxy compound, and it leaves behind a layer on the surface of the steel. And just that ever such thin layer of oiliness that comes after the extrude honed is enough to completely and utterly stop the nitriding process. Look, there is no impact at all of the nitriding process. You might as well have not even bothered putting the dye in the reactor. If you clean the extrude honed with alcohol, you think you've done a pretty good job. It looks pretty clean, but look, it's still an outlier. It's good, the surface is good. If you hit the surface with a surface indenter or scratch it with a file, you'll get the same result. But under the surface, subsurface, it's really not nitrided to anything like the same depth. All the ones that have got hand polishing on them go well. So a final hand polish is really quite important prior to going into the nitrider on the bearings. But please, polish is the key word here. Polish and clean. This is not grind away massive amounts of steel. So really, ANSI 600 or ISO 1000 paper, you're trying just to remove dirt. You do not want to move steel. But if you get it right, like wire cut and hand polish, which is how your die makers will deliver it to you with the first nitriding, you can see we get a fantastic curve compared to the ones with a greasy surface. Now, your die vendors, they know this pretty good. There's actually data in this presentation from Thumb Tool. There's data in this presentation from Exco and from Cast Tool. All three of those organizations do a lot of nitriding, and they know their stuff pretty good. The problem is keeping these dies really clean when they go into the nitrider. And what can go wrong is we lose our steel catalyst. Without the catalyst, the ammonia doesn't dissociate, and there is no nitrogen. So there's two things that can go wrong. If you take the nitriding so it's too thick and you have a poor contact between, a poor layer between the diffusion layer and the actual bulk of the steel, you can get this flaking. This is a picture of a die actually from South Wales in the UK. And this was a double problem. One, we were too aggressively nitriding the die, but secondly, when the die was removed from the die ring with the baffering left piece of aluminum on the die, they were cold shearing it off the die face, and that put additional stresses into the layer and caused this peeling of the steel. There's also some suspicion that when it went in for some of the nitriding processes, the die may not have been as clean as it should have been. If we look at the corners here, when you get right to the corner, you've got nitrogen coming in this way, up and down, but you've also got nitrogen coming in from the side. And you can, if you're over aggressive with your nitriding, produce this extra layer of the wrong phase, because the corner is subjected to twice as much nitrogen coming in as the straight faces. This causes microcracking, it's weak, and as soon as it hits an extrusion, it chips out and looks like this. And this is what it will look like on a die. I haven't seen that very much because I believe with systems like Nitrex and other people who have automated nitrogen gas nitriding, we don't go that crazy anymore. Back in the days when these things were just chucked into a bath of molten cyanide and left until lunchtime or dinner time to come out, there wasn't the same process control. But poor nitriding and dirty nitriding leads to flaking, chipping, chip bearings, and flake bits that come off the die, like the left-hand side. They can actually get into the die bearings and cause problem themselves as abrasive particles. Now, there's a small tail. It wouldn't be me if I didn't have a small tail. I was working for a while with Hewlett Hydro down in South Africa, and we were working with their nitriding. And we always like people to wear gloves when they're loading the dies. And one guy decided, for whatever reason, not to wear gloves this day and left a greasy fingerprint on the surface of the die. And you would think that would have no consequences whatsoever. In fact, it didn't harm the die in any way. It's just that there was no nitrogen atoms formed where the grease of his fingerprint was on the surface of the die. It looked no different at all when it came out of nitriding. But after it had been to the press several times, that particular area of the die had been subjected to some wear with the aluminum going over it. And you could actually start to see the image of his fingerprint on the die. Now, we were very tempted to get out our junior detective kit and go and work out who it was, but we decided to let that go. But it was just an interesting exercise. But I'm really sad that the pictures of that have been lost in time since we Hewlett Hydro ceased to be a hydro facility and went back to Hewlett in South Africa. Somehow the pictures didn't make it. We can also get this. This is fairly high magnification of the surface of the die. These are cracks which are caused by cleanliness issues in the die. This is where the compound that's on the die is itself diffusing in the die and causing problems. So we really need, cleanliness is really next to godliness. And so we need to get the right amount of nitrogen at the right temperature. We need to get a thin, controlled white layer. Thinner the better. If it gets too thick, it will chip off, it'll craze, horrible. We need a deep enough diffusion zone that if there is somewhere, there's still some good hard steel behind it. And we need a good transition layer between the diffusion zone and the seal substrate so that that doesn't peel off. Last thing from me on this. If you have a bridge die and you're regularly nitriding the bridge and the plate, once there is some cracking in the webs, stop nitriding the bridge. The reason being, when you nitride those cracks, nitrogen will get down in those cracks and it will make the crack tip more brittle and the crack will grow faster. So once you start getting cracking in a hollow die on the bridge, and thank you to Rio Tinto for use of this picture, those cracks will grow much faster if you continue to nitride the mandrel. By all means, nitride the die plate. But long before you have any wear out issues, these cracks will grow to the point that the die no longer works.
Yeah, this is another example of overnitriding. This is not re-nitrided surface. This is a nitrided surface actually of a die cast tool, which is subjected to like thermal shock. This is about 10 thou, 8 to 10 thou of nitride layer. When you get to 10 thou of nitride layer thickness, it's you start to feel that the thickness is, the nitride is too thick, and then when it during the thermal shock, it will crack. And then because the nitride layer is has different thermal expansion, it expands differently than a steel. It can crack because it's more brittle. And then when the crack you can see is the same as the thickness of the nitride layer. So if the crack is bigger than the critical crack size for that material, the crack can grow and then go through the whole tool and then break the tool. So this is also one of the problems with overnitriding. Here, another reason for the failure is that there's like a narrow transition zone compared to thickness of the nitride layer.
So getting everything controlled and keeping it within limits is very important. Now, we're not giving you numbers deliberately because every gas nitrider I've ever seen made by each company is different, but they have computer control systems and you set them up with them to get you right in where you saw that red dot that Yaya showed you in the control field between temperature and gas dissociation. The computer will do its thing, but if you put dirty dyes in, the computer can't compensate for that. So cleanliness is, I keep repeating in this, is next to godliness for nitriding.
Yeah, as Richard said, clean dyes, surgically clean. Richard's always.
Yeah, in fact, one of the things that we have a process in many of the plants I've worked in, where the person putting the dyes into the nitrider will wear white gloves. And if when they're finished loading the nitrider, the gloves aren't still white, then those dyes were dirty and they need to come out and be cleaned again.
Yeah, other reason for wearing gloves is probably you don't want to leave your fingerprints there.
Prints. Oh yeah.
So everyone knows that was you.
Yeah, CSI will get you one way or the other.
Okay, the correct volume of a steel in the reactor, because these reactors are designed to be full, and the programs has been designed to be to give the service to full reactor, not half loads. And process, correct gas mix to have a dissociation, correct temperature, correct time. It's all matters. And then at the end, you have to trust but verify. What that means, you have to run test blocks in your Nitrider and send for testing those test blocks to make sure that you get a nice hardness profile and your indenters makes like clean indentation. And we also once in a while do test on the random parts. You can maybe just take a random die and then just do a destructive test on it.
Not recommending the extruder though, but at the die shop it's good. But the regular testing of a cube of steel, and you can get these test pieces from most die suppliers that I know. So we'll supply these either free or for a small charge, and then you put them in with your nitriding charge, also making sure they're clean, and then a lab somewhere can cut them up and investigate to see how good that nitriding was.
Yeah, the reason I'm telling this because it's to simulate, or sometimes we can simulate the bearing with our samples. So because so if you just give a cube sample, it's gonna be outside of the sample, so it's gonna be nitrided very well. But inside the bearing, it's a little bit harder for nitrogen to reach. So maybe we can give something like that, something like dye to be tested for nitrogen.
So with all that information and with a good nitrider and a computer control, you can really do a good job nitriding the dye. But I hope we've shown you as well that if you don't control the time that dye spends in the preheat oven, it doesn't matter how good a job you did nitriding it, you've destroyed it leaving it in the preheat oven. So from an extruder's point of view, which most of you are out there, I believe, things you control. I mean, you send the dye off for nitriding, either internally in your dye shop or externally for someone to nitride it. And we have to have some faith that that equipment is good equipment and it's properly run by a computer. But when the dye is in the plant and it's been put in a dye oven and forgotten, or something's happened, the press has broken down, but we didn't cool the dye ovens down. The dye spends more than 12 hours in there at temperature, you're beginning to damage your nitriding. And the point being, your nitriding layers build up. What you put in nitriding number 1 is what's pushed in deeper during nitriding number 2 and pushed in deeper during nitriding number 3. So if we destroy all of the surface nitriding in number 1, the next time we nitride, we go back to number 1 again. We don't build up 1, 2, 3, 4, 5 like I showed you earlier. We just keep doing number 1. And in doing so, we do have a well sub-optimized nitriding procedure, and our dyes will suffer. So the first thing for me that's really important from an extruder's point of view, to keep a good nitrided dye and to make the dye life longer, reduce our costs, and of course a well nitrided dye will give you a better surface quality. We really need to respect the time the dyes spend in the preheat ovens. Next is when we clean and polish the dyes after caustic. Please, 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 nothing rougher than 600 a grit ANSI or P1000 ISO. I've done a lot of tests. Anyone want them, I'll send them the papers from ET16 on the subject. We drove a veteran die corrector of some 30 years crazy just polishing some bearings and measuring them. We checked it out, and it's not a matter of how skillful you are. I've had a lot of die correctors say, well, yeah, a beginner needs 600, but I'm skilled, I've got 240. It's nothing to do with that. 240 is sufficiently aggressive that it removes steel. We don't want to remove steel. The bearing is exactly how we want it when it arrives. Now, if you're die correcting, 240, great, because you want to remove steel. Sorry, I keep pushing this, but it's one of my great drives. I haven't said the word alignment yet today, so I'm more pushing on abrasive paper. Next, keep your billet clean. If you put your billet in with a whole load of road dirt and sand on the outside of it, then you're going to be pushing abrasive through your die bearings. But most importantly, with respect to today, create a re-nitriding schedule based on the distance extruded, number of feet out of a cavity. Do it that way rather than the number of billets extruded, and respect those rules. If you do that and you re-nitride at the correct intervals, you don't bake them in the oven too long, and you don't beat them to death with rough sandpaper when you're bringing them out of the caustic, your dyes will last longer. You'll be using your dyes for a longer period of time, getting better value out of them, and getting better value out of the net operating capital you have invested in all those dyes you have out there on the racks. Please, when you walk around a plant sometime and look at those racks full of dyes, and I mean some plants have a serious number of dyes in racks that are visible from the press, try to remember each one of those is a precision tool made by very expensive equipment, and those dyes are the lifeblood of our business. So please treat them with respect, nitride them, and look after them properly. That's us today. We've run over 7 minutes. I hope that's okay with folks, but we're open for questions now. Lisa will take over as our maitre d' or whatever, and bring some questions forward.
We do have a question, gentlemen, and that is, can you explain what you mean by re-nitriding after a distance and not a weight?
Okay, that was what I said. So some people will say when a die has extruded 500 pounds or 1,000 pounds, we re-nitride it. Well, if that's a 2-inch round bar, that's not a lot of metal gone over the bearings. If it's a 50 thou or 60 thou glazing clip, that's a lot of metal gone over the bearings. And so when I mean re-nitride by distance, when you say you've got a 100-foot run-out table, then you want to do your re-nitriding based on how many feet of extrusion has gone through each cavity, not the number of billets and not the weight of billets that's been extruded, because you've got multi-cavities. So when I say extrude by distance, basically add up the sum total of all the extrusion lengths that have come out through that cavity, and when you get to the number, then it's time to re-nitride. Sorry, I wasn't clear about that.
Okay, we had another question come in, and that is, any recommendations on number of feet extruded per hole before nitriding or re-nitriding?
We're putting us in a very difficult place there, because every company has its own proprietary numbers. And one of the things I'm very, very careful about is I don't share anyone's data without their express permission. I've been at too many extrusion plants. I'd probably find myself hanging upside down from a flagpole if I gave away people's secrets. There are some guidelines, I think, in the AEC die manual, but I'd have to look to get the exact numbers. But we've deliberately stayed away from saying after so many feet do this. One, because your business is unique, and two, we don't have any generic numbers because everybody's so different. If you're making little thin 40 thou wall glazing clips day in, day out, it's very different than somebody with a much larger press who's making a 4-inch round bar for machining. So it really needs to be developed for your business. But I'm absolutely certain your die vendor and maybe even your billet vendor will work with you to go through a process where you work out what are the correct numbers for your particular business. I'm sorry, it sounds a little bit of a cop-out, but the only numbers that I know as numbers belong to other people, and I don't have the right to share them.
Yeah, it also depends on what alloy you're extruding. If it's 6082, it's different than the 6063.
Okay, we'll give it a couple more minutes to see if anyone else has any questions. But meanwhile, I'd really like to thank you both, Richard and Yaya, for yet another terrific presentation. As always, you deliver the goods. Again, any questions that come up after we close today, by all means, reach out to Yaya or Richard or myself. You can see their contact information on the screen. We have recorded today's webinar, and we should have it posted within the next few days for viewing for the future. We'll also, as usual, be sending out our evaluation survey for the webinar, and you should receive that within the next day. And we ask that you please participate in that survey because we do depend on your input. It's very valuable and helpful to us in developing future webinars, live events, podcasts. We want to bring you what you want and need to see and hear. So we depend on that, that input greatly. Remember to visit aecmeets.org regularly to register and for details on upcoming events. Oh, we do have another question. Between 6 and 12 hours of nitriding cycle time, is there an ideal number?
Yaya, any comments on that?
I think 12 hours is too long. It depends on what temperature and then what mixture.
I think this is where having a block in your system is good, because both time and temperature will impact the growth of the white layer. And whilst a longer cycle may seem like a good idea, if it produces a thicker white layer on the surface, it's not a good idea. So that's why I think when you're developing your process, and if you buy a machine from Nitrex, they come in with some pretty good sort of numbers, as do other manufacturers. I use Nitrex because it's the only manufacturer's name that comes to mind immediately. But you want to have these traveler blocks go through, have them investigated, and if the white layer is too thick, then you need to adjust your dissociation constant and temperature appropriately. If you have no white layer and your diffusion layer isn't enough, you need to build it up. I'm again afraid that I don't have specific numbers for you to do, because again, people are different. And reactors, if you've got twice as much steel in a reactor, it will be a different answer than if you've got a smaller reactor, because the surface is what controls the dissociation constant.
Okay, thank you. Just some comments on upcoming events. If you have your AEC calendar of events, we did have challenges front to back variations with increasing billet length by none other than Richard Dixon and probably Paul Robbins and Yaya of Castool. We're going to put that one off probably until later in the fall. We'll keep you posted on that one. We do have scheduled for September 29th a safety webinar. The presenter will be Gary Higby of Safe Start. And we've got our, sorry about that. We've got our upcoming Aluminum Summit, which will be in Nashville, Tennessee at the Sheraton Music City Airport Hotel, September 14th through the 16th. We have the long-awaited press maintenance workshop coming up in Atlanta at the Sonesta Atlanta Airport Hotel North, and that's October 18th to the 20th. And rounding out the year, we will have our safety summit in Rosemont, Illinois at Lowe's Chicago O'Hare Hotel, November 9th and 10th. The AEC and Aluminum Association will be co-hosting that event with a jam-packed lineup of safety professional presenters. And so we're very excited to be bringing you these upcoming live events. Don't forget about ET. That's coming up next May, and we are getting that all in order once again. And we're really excited and looking forward to that. It's going to be our 50-year celebration of ETs. So that's going to be very, very exciting and in a wonderful place, the Hilton Orlando in, of course, Orlando, Florida. I don't think we have any more questions coming in. So gentlemen, thank you so much for your wonderful presentation. I'd like to thank everyone for being with us today. And we look forward to seeing you in person at one of these upcoming live events. And of course, we hope to have you with us at our upcoming webinars. We'll keep you posted on those. And again, check aecmeets.org often for details. Thank you again. I think
Thank
that's
you,
it for
Lisa.
today.
Everybody
Thank you.
stay safe, and hopefully we'll see you in person somewhere in the not too distant future.
Absolutely. That's all for today. Goodbye.